I'll make sure that everything works.
Okay. So generally speaking, good job on the exam. The average was almost 10 points higher than the last two exams. Yeah. So last two chapters are really short, and this one in particular is actually a lot of review. The first part of it's a lot of review. Um, okay, so amines, the name of the game here is nitrogen. So amines are derivatives of ammonia. That's one way to think about it. Or you could just say that they're substituted nitrogen atoms. But so this is ammonia, NH3. If we start substituting hydrogens for our groups, whether they be alkyl groups or whatever, we can start making other kinds of amines. So this is NH2R. And so this is a primary amine. We add another R group. So now we have NHR2. That's a secondary amine. And then unsurprisingly, if we have three R groups, NR3 is a tertiary amine. We can also actually go one step further. So before I do that, let's go back to ammonia. If we take ammonia and protonate it to make NH4, that is ammonium, the ammonium cation. We can do the same thing to any of these other amines, but maybe most notably if we add a fourth R group, notice here there's no lone pair on the nitrogen. This is NR4 plus, and we call this quaternary. And so it's a quaternary ammonium salt because there's going to be some sort of X minus counter ion to balance the positive charge. So I've only drawn NH4 plus and NR4 plus, but of course you can add multiple, well, you can add another hydrogen or another R group to any of these in the middle and sort of make these mixed quaternary compounds. So there's two ways that amines can react, generally speaking. They can act as bases. So if we have, that's a tertiary amine, but it could be anything, could be ammonia as well. And we have an acid. this is just going to be an acid-base reaction. So we're just going to deprotonate the acid. So we protonate the amine and make an ammonium salt, and then we have a chloride anion to go along with that. So amines make pretty good bases. They can also be nucleophiles. And both of these sort of ways that amines can react have to do with the lone pair. So the lone pair is required for the amine to be basic because that's what deprotonates the acid. And in the same way, that lone pair is also nucleophilic. So instead of hydrogen chloride, let's use methyl chloride or chloromethane. And we're going to do really the same thing here. We're going to have the nitrogen, in this case, attack the carbon. And we'll kick off a chloride. This is just an SN2 reaction. And so we get R3N CH3 with a positive charge, and again, the chloride counterion. So those reactions are really the same. It just depends on whether you're attacking a carbon atom or a hydrogen. This specific reaction here is called an alkylation because we're adding an alkyl group to the amine. It's actually a little bit more complicated than that, and we'll get to that in a moment, but I just want you to see the two general types of things that amines can do. Okay, we're also going to talk about geometry. We kind of have, we haven't really talked about this for many of the other functional groups, but there is some interesting stuff that amines can do in that regard. So those sort of regular geometry for an amine looks like that. The nitrogen lone pair and the three R groups or hydrogens or whatever mixture of those two. So that's 4 total electron domains. This is going back to Vesper theory from Gen Chem. And so we have the electron geometry. We've got 4 electron domains. So that's tetrahedral. But the molecular geometry takes into account the fact that one of those electron domains is a lone pair. And so the molecular geometry is trigonal what? Say it louder. Yeah, pyramidal, whatever. As opposed to trigonal planar, because if it was planar, you don't normally have 3 electron domains. And I think you can see how the lone pair pushes those 3 groups down a little bit. So carbon is also tetrahedral in sort of this same way. And if we have 4 different groups attached to a carbon atom, that carbon is chiral. So if we have 3 different R groups attached to the nitrogen, you can also say that maybe the lone pair is also kind of like an R group. And so the lone pair plus three different R groups, that those are all different things. So if all three groups are different, then that means that the molecule is going to be chiral at the nitrogen atom. So that means the nitrogen atom is a stereocenter. So you can assign R and S, et cetera, et cetera. However, well, let's show an example of that actually first. Okay, so those two molecules are not the same. They've got the same things attached to them, but the stereochemistry is different here, and so these are enantiomers. There is a caveat there, and that is that if you heat one of these molecules, you can actually cause essentially an equilibrium process that causes the two to interconvert. Now, what does that look like geometrically speaking? Okay, so there's, let's say, our first enantiomer. We've got that trigonal pyramidal geometry where all three of the R groups are sort of pushed to the left a little bit. We can go through a transition state that is more symmetrical, right? So there's a line of symmetry up and down. This is sp2 hybridized, whereas regular nitrogen with the lone pair in that orbital is sp3 hybridized. So this molecule is chiral. This one is achiral. This is kind of an intermediate or transition state. And now what we can do is, so the R groups were previously sort of on the left. Now they've been scooted up to being sort of perpendicular or perpendicular to the board. And now we can push them off to the right. Like that. This is now a mirror image of what we started with. Nitrogen is sp3 and is chiral. So if we said that the stereochemical configuration of the starting amine was R, then that means that the product is going to be S. And the only thing you need here is a little bit of heat, because that's sort of the kind of an energy diagram. That transition state in the middle is higher in energy. But the difference is only about 25 kilocalories per mole. And that's pretty easy to do at room temperature. So what actually happens, and when you've got a flask of some sort of amine just in the laboratory, it's going to be a mixture of both of these stereoisomers, and they're going to interconvert between each other. If you actually want to be able to isolate one of the isomers, you usually have to cool it way down, to the point at which you can no longer get over this energy hump, and then they get locked in their configuration. So not really. Yeah. Like you don't need to memorize that it's 25 kilocalories per mole. Just know that that interconverts in between the two enantiomers. Okay. Okay, several methods for making amines. The first three we've already seen, and so this should be a review. And then the last three are going to be sort of slightly new ones. So first of all, we can make amines from alkyl halides. This should look very, very familiar if you had just gone over your exam. So we start with an alkyl halide and we go through a nitrile. So to make a nitrile, we need sodium cyanide. That does an SN2 reaction at the carbon. So there's the installation of the nitrogen atom that's going to become the amine. But right now it's part of a nitrile. Then we use lithium aluminum hydride, and that's a reducing agent. And so that reduces our nitrile to, in this case, a primary amine. Again, this process adds a carbon from the cyanide, right? But that carbon that's part of the cyanide is added onto the molecule. So we went from a C3 molecule. The starting alkyl halide has 3 carbons, and the product has 4 carbons, right? Okay. So we can do that. And then, of course, this also includes from alkyl halides, also includes from nitriles. We know how to do that. So we can start also from carboxylic acid. This has an additional step. So the first thing we'll do here is use thionyl chloride, and that makes what functional group? Yeah, acid chloride. Then we'll add our nitrogen source, ammonia. What functional group do we get now? What? Yes. But attached to the carbonyl, that's an amide. And then we reduce with lithium aluminum hydride. And we get our primary amine. We can also go back to chapter 18, I think, and do electrophilic aromatic substitution to make aryl amines. So if we start from something like benzene or some sort of benzene derivative, we install a nitrogen by doing a nitration reaction with nitric acid and sulfuric acid. That gives us an NO2 group. And now to reduce to an amine, a method that I haven't really talked about yet, but we can use for this is to do a hydrogenation. So we need H2 and then a palladium catalyst of some kind, which we just abbreviate as PD. Then that gives us our amine, and this is an aryl amine or an aniline, because that compound, just benzene with the NH2, is called aniline. Okay, so you'll notice that all these have made primary amines. That aryl amine is also primary because we've got only one R substituent on the nitrogen. And primary amines are great, but we might want to make something with more substituents on it. So one way that can be done is by alkylation. Well, I say that, this ends up being a really sucky process, but we'll see why in a second. So if we take our ammonia and an alkyl halide of some sort, in this case, I'm going to use methyl iodide. So that's usually what's used instead of methyl chloride or chloromethane. This is the same example that we saw at the beginning for the nucleophile example. So we do an SN2 reaction at the carbon of the alkyl group. And so we get that compound with an I minus. Then we lose a proton, make HI, hydriodic acid, and then we get NH2 CH3, which Breaking Bad fans will know as methylamine. The tanker car. Yeah. So that looks great, right? We just do this alkylation and we get a substituted amine. The problem is when we compare these two amines, ammonia versus methylamine, substituted amines are more nucleophilic than ammonia. So why is that a problem? Well, in the beginning, we're using NH3, ammonia, as a nucleophile to react with methyl iodide. And what we generate at the end of that reaction is a better nucleophile which is now going to go back, find any methyl iodide that's still around, and react with that before another molecule of ammonia can get to it. So what actually ends up happening when you do this process, and I'm going to abbreviate it a little bit here. So NH3 plus methyl iodide gives us methylamine, MENH2. Same thing as NH2CH3. Methylamine is a better nucleophile than ammonia. So it's going to react with another equivalent of methyl iodide, do another alkylation to make dimethylamine with 2 methyl groups and 1 hydrogen. And guess what? Dimethylamine is more nucleophilic than methylamine, which is more nucleophilic than ammonia. You see where this is going? So we alkylate again. Trimethylamine. And you think, okay, well, that's as many alkyl groups as we can add on, right? It's like we can make those quaternary ammonium salts with 4 R groups, 4 methyl groups, a positive charge, and an I- counterion. So you cannot stop in the middle of this process and say, oh, okay, I know what I'll do. I want to make dimethylamine, Me2NH. So what I'll do is I'll just add 2 equivalents of methyl iodide, right? What would happen in that case is you'll first make methylamine, which will then alkylate to dimethylamine. And now you have ammonia competing with dimethylamine. The dimethylamine is more nucleophilic, and so it'll continue all the way to tetramethylammonium iodide at the very end. So if you do that, if you just add 2 equivalents of methyl iodide, you'll end up with half of your ammonia converting all the way to the quaternary ammonium salt, and half of it doesn't react at all. So essentially, this process is not useful for making any of the lower substituted amines. However, if you want to make those quaternary ammonium salts, this is a perfect way to do that. And in fact, those molecules are kind of important. One example is something that looks kind of like this. I'm not counting the carbons very precisely. I think most of the chains are actually 8 carbons, but you get the picture. There's a compound that looks like this. It's got a methyl group and some longer alkyl groups, and then a chloride anion. And if you have a reaction that's in 2 phases, like when we did the Wittig reaction, we had I forget which solvent it was besides water. Anyway, we had an organic in an aqueous layer, and you had to stir them really well to get the reaction to happen. Another thing you can do is add a little bit of a quaternary ammonium salt like this, which is polar like water because it's made of ions. And it's also nonpolar because it's got those hydrocarbon chains on the nitrogen. So if you take a 2-phase mixture and add enough of this stuff you can actually get the two layers to mix together. So you can get water and an organic solvent to make one phase. Still, would be kind of hard to make with this reaction because you've got different alkyl groups, but whatever. Okay. The next method is using azides. This is a new functional group that you probably haven't heard of before. But if we take an alkyl halide and react it with NaN3, looks very strange. NaN3 is sodium azide. So it's Na plus, and then the azide ion, which is N3 minus. Looks like that. Kind of cursed. And even better, it's toxic and explosive.
It really just bundled everything it could together. didn't it?
Seriously, yeah. So if you treat an alkyl halide with sodium azide, you end up with just attaching that ion to an organic group. So we can also write this as R in 3. Again, these are just as, actually the organic ones aren't super toxic, but they're still explosive.
It's like in the real world.
Yes.
what would someone
Because one of the other methods above might not be compatible with the functional groups, the other functional groups in your molecule. So if R is really complicated, this might be an effect. Make sure you do it in dilute conditions, because the big issue, especially with sodium azide, is in the solid form.
Sodium does not look any moisture for the most part.
Yeah, it's Na plus though. That's not that's the main issue. And actually, we're gonna get to this at the end, kinda. But I'll mention it here. Is what does just like regular nitrogen look like? The structure. So nitrogen is diatomic, right? N2 when it's just in the air. So that looks like N triple bond N. Oh, look, we've already got the beginnings of a dinitrogen molecule. It's already got a double bond. And so this molecule is so stable. I didn't mean to make a rectangle, but that works. That molecule is so stable that the azide will do anything to make nitrogen gas. So when a solid suddenly and quickly makes a large quantity of gas, that's called an explosion. And so the driving force for the explosiveness of this and for the next reaction, which by the way is hydrogenation with H2 and PD. That makes an amine. And nitrogen gas. So obviously you have to do this pretty carefully. But there we go. And that makes our primary, again, in this case, amine. So draw me the structure of the intermediate in the middle there, and then the final product. So sodium azide replaces the halogen with an N3 group, which you could draw out if you wanted, but I'll just call it N3. And then we hydrogenate with hydrogen and palladium, and that reduces the N3 to an NH2.
Do you still keep the extra nitrogen? Yeah.
Sure, if you want. Okay. If you thought we were done with carbonyl chemistry, I'm sorry. Because reductive amination is probably the best way to make substituted amines. So I kind of already said this before and then didn't do what I said I was going to do. But so primary amines, this makes really substituted amines, primary amine. Okay, so all of these methods we've talked about pretty much are for making primary amines. And then once you have your primary amine, if you try to alkylate it, it just does that uncontrollable process thing. So how do we get around that? We use reductive amination. So in reductive amination, well, the name implies that we're going to put an amine on something and we're also going to reduce it, which is the case. So we start with a carbonyl compound, and then we replace the oxygen with a nitrogen. And so this NH3, here you can use, of course, NH3, primary or secondary. Not a tertiary amine for this process, though. And that'll make sense in a second. So we had acid and our amine of some sort. We go through an intermediate called an imine. And then with hydrogenation conditions, the imine is reduced to an amine. Now, this example makes a primary amine, but that's entirely dependent on what nitrogen source we use in the first step. So essentially what happens is we attach everything in that nitrogen-containing molecule except one of the hydrogens. Okay, let's look at an example. Let's use methylamine as our nitrogen source. I'll skip the imine intermediate. Just looking for the product here. So, just like with the rest of carbonyl chemistry, we should draw all of the part of the molecule that isn't related to the carbonyl. Okay, so what do we do? Well, the carbon that used to be the carbonyl carbon is going to get reduced so that, okay, this carbon here, and we attach the nitrogen atom along with everything attached to it minus one hydrogen. So that means what we're going to attach is MENH. There's our attachment. And so all we have to do here oh, that's the edge of the page, is put our methyl group and our hydrogen. So this is
Instead of drawing it out, that's pretty accurate.
yeah, that's fine. So you could write that. You could write that. You could write that flipped around the other way. Yep. That last way is probably the way most chemists would draw it, but it doesn't matter. Okay, so give you a couple of examples to work on. Actually, one more thing. Again, not necessary, but it may help you to draw out this extra hydrogen that gets added to what used to be the carbonyl carbon. That's where the reductive part of reductive amination comes from. Okay, so in all of these cases, your structure is going to start with everything except the carbonyl. The carbonyl is now going to be a single bond instead of a double bond. And the atom at the end of that single bond is going to be a nitrogen. So the other stuff attached to that nitrogen is going to be, well, the stuff that it was attached to in the reagent minus a hydrogen. So the first one uses diethylamine. So if just we remove a hydrogen, that means it's going to have two methyl groups on it, like so. Or you could write ethyl groups, ET. Yeah. Yeah, that's fine. So you could write ET2. For the next one, we've got a benzene ring on the nitrogen with two hydrogens. Subtract one hydrogen, so we still have one hydrogen left. Ring like that. Or we can replace the benzene rings with phenyl groups and write something that looks like that. Okay, for the last one, we've got a ring. The nitrogen atom is in a ring. And so you can just treat each side of the ring sort of like a substituent. So we include everything in this molecule except a hydrogen. There's only one hydrogen. And so that means that we're going to take the ring, essentially flip it upside down. And we have that. Are we happy with that?
I got the same answers if you ever must be the hydrogen that I put.
Yeah, don't forget to take the hydrogens away. Another way to check yourself to make sure you've done that correctly. Huh?
Where you add the stuff?
Oh, this one? Do you have to? No. It may help you keep track of things. So I would say it's not a bad idea, but there you go.
Is that like secretly where the other hydrogen will take away goes?
The other hydrogen that we take away.
What we're
Sure. Sure, you could call it that. So check your answer. Nitrogen needs 3 bonds and a lone pair. I have been naughty and I haven't drawn my lone pairs. Not super required unless you're doing a mechanism of some kind, which we're not really going to talk about. But if your nitrogen has 4 things attached to it, it's got to have a positive charge. And so that's not going to happen when you do this chemistry. So make sure your nitrogen has 3 things attached to it. Questions on reductive amination? All right. Happy Thanksgiving. Thank you.